we have already established that in order for a limit to exist, the left and right limits must be equal. Okay? So now I'm going to ask you to find the one-sided limit. And then I put a little parentheses here because this is where people tend to lose everything they've just gained in this section. Just forget about this for a second. Look at this function. If I had given you this function and asked you to find the limit as x approaches plane 3, in the previous section, what would you have tried to do to it?
Plug it in.
Plug it in, and you would get 0 over 0, right? That 0 over 0 usually indicates a what? A hole. 0 over 0 usually indicates a hole. Indeterminate form usually indicates a hole. And when there's a hole there, we can remove it. There is nothing about this function that should make you think that it's going to behave in a way that would have a jump. Do y'all understand that? It's not absolute value, it's not a piecewise function, it's not a square root function. It may have asymptotes and it may have holes, but there is nothing about it that's going to make us believe that there's anything weird going on so that the limit shouldn't exist. The limit only does not exist when what? Left and right aren't equal.
And when it jumps.
When it jumps,
Oscillates.
when it oscillates. And we also know now that if it's outside the domain, the left and right limit can't be equal, right? But there's nothing that makes us think any of these things have gone on. So even though I'm asking you to find the limit as x approaches 3 from the left, you can treat this particular problem like it doesn't matter what side I'm asking you to find. Because if the limit exists and we can prove that algebraically, we don't have to worry about left and right sided limits. They automatically are equal to each other and to the actual limit. So because there's no reason to believe this limit would not exist if it were just approaching plane 3 rather than from the left, we're going to treat it algebraically just like we would the ones before that yielded 0 over 0. I'm going to try to factor and cancel it. If I have 3 minus x over x plus 3, x minus 3, these two guys right here cancel, but they don't cancel to 1. What do they cancel to? Negative 1. They're opposites. They cancel to negative 1. So I have just proven algebraically that this guy is equal to this guy. Thank you. And now, if I resubstitute the limit, I actually get a limit. What is it? So that means that the limit as x approaches 3 is negative 1/6. And I can algebraically prove that by direct substitution after I factor and cancel. So because of that, this is just there to throw you off. There are only certain times when it even matters whether you're coming from the left or right. And that's going to occur on piecewise functions, greatest integer functions, things we know have jumps in them, the ones where we have like absolute value of something over itself, but not the absolute value. And you will learn a list of those things to look for. Piecewise functions are going to be your primary. Square root functions are weird because the domain is so limited. But other than that, you treat them. If you can algebraically do what we have been doing to it and you can get a limit, that is the limit. Understand? Okay. So we are going to now look at these three. So if I'm looking at this function, if I have access to a graphing calculator, I'm probably going to put it in my graph and just kind of take a look at it too, just to be sure nothing kind of squirrely is going on there. You know that it's not at the edge of a domain. So that's probably what I would do. Now I would take a look at the graph first, make sure nothing weird looks like it's happening as we approach 2. So we've looked at the graph and we've seen that it doesn't look like anything strange is happening there. So we think that maybe we could find this limit by direct substitution. So let's plug the 2 in, and what do we get?
Square root of 2 minus 2
Over negative 2. Well, it's an odd limit, agree? But it's a number. So even though we're plugging in from the right, when we look at it algebraically, there's nothing to suggest that there's any reason that that limit wouldn't exist. There's no jump, there's no oscillation, there's no, what am I looking for? It's not piecewise. We don't even think there's a hole there. You know, there's nothing. We're not at the edges of the domain. We think we're pretty good. So technically, this is about as far as I can go, right? About. I mean, we could algebraically play around with that if you really wanted to. But usually we don't leave a negative on the bottom. So usually what we'll do is we'll float it up to the top and distribute it. So you might see this answer instead. So it didn't matter that we were coming from the right because nothing strange was going on in that function. So for part C and part D, we'll look at C first. We have the limit as x approaches 4 from the right of the absolute value of x minus 4 all over just plain x minus 4. And we've already encountered this one. And by now it should be in the back of your mind as it doesn't look like it's going to be, but it turns out to be a piecewise function with a jump in it. You guys have seen it enough to know that when x is what number? 4. When x is 4, we're going to get 0 over 0. And most of the time when that happens, when you get 0 over 0, most of the time it's a hole and you can remove it. But there's always a possibility that it's not a hole. And we don't know anything algebraically we could do with absolute value, so you're probably going to have to look at it graphically. And so when we look at the absolute value of x minus 4 over x minus 4 graphically, everything to the left of 4 equals what? Negative 1, right? Like that. And everything to the right of 4 equals
Positive.
So does your graph look like this?
Yes, ma'am.
Yes, okay. So, you know, your first instinct when you see 0 over 0 is probably to start attacking it. Let me try to factor it. Let me try to rationalize it. But you need to be careful with absolute value because they do behave like piecewise functions and there could be a jump there. So you just kind of train yourself when you see those or something you're not really comfortable with, look at it in a graph first. So if we come in, x approaches 4 from the right, what is my limit? And that's all there is to it. And if we come in and approach 4 from the left, what is my limit? Negative 1. So part D is negative 1. So what could we say about the limit, the two-sided limit as x approaches 4? Does not exist. Okay, so now we want to find the limit as x approaches 2 from the left of the square root function x minus 2. We're also going to find the limit as x approaches 2 from the right of that function. And I'll just go ahead and teach you now that if it is a standalone square root problem, you're going to have problems where it goes to 0. You're going to, because the domain is limited there. And it's limited in a huge way. Not like with a vertical asymptote where it's just one little spot. This knocks out entire chunks of the graph. So if we think of this graphically, the square root of x minus 2 looks like this. You guys understand that? Okay. Now, I'm tempted, and I'm sure you are too. You just say, oh, I can just plug 2 in, right? And I get the square root of 0, and that's 0, and you would be very tempted to say that both of these are 0. But you have to know enough, and that's why there are no pat answers in calculus. You have to know enough to look back at it, to figure out what's going on, to investigate it. But if you do enough practice, you will learn there are certain ones that cause the problems. It's the absolute value functions. It's the square root functions. You know, the ones that look algebraic can be fixed algebraically, but the ones that don't can't. And so even though I got 0 when I plugged in, you have to know enough about square roots to understand that you are at the edge of your domain when it goes to 0. Because once it goes negative, graphically it doesn't exist anymore. Make sense? Okay, so that's one you're going to want to flag. So let's talk about it. From the left, what is the limit actually here? It doesn't exist, yeah, so we can't say that, even though we got that by direct substitution. So direct substitution will occasionally lie to you. But from the right, as I approach this guy, I'm okay. It really is 0. So what happens here most of the time, is that one of them actually will be 0 and the other will be does not exist. And we saw that a little bit with that semicircle we looked at. There were 2 spots. From the left, this one doesn't exist, but from the right it does. And from the left, this one does exist, but from the right it doesn't. So you're going to have to adopt a more graphical approach to math. So I'm sorry about that because I know you don't like it. You want something fast and easy. But you're going to have to take your time and just kind of think it through, and you will do fine.